Hello, everyone, and thank you for joining us today. My name is Karen Bartos, and I am a Technology Manager at the NASA Glenn Research Center. Our NASA Technology Transfer Program webinar today is on Glen's Microwave Power Combiner. Our presenter today is Dr. Rainey Simons. Dr. Simons is a research engineer in the Advanced High Frequency branch at the NASA Glenn Research Center. Dr. Simons began his NASA career as a National Research Council postdoctoral research associate in 1985. At Glenn, he has served as the chief of the Electron Device Technology branch and as a senior microwave and antenna systems engineer. Since November 2017, he has served as the program officer for the maturation of instruments for solar system exploration and the Planetary Science Division for NASA headquarters. Dr. Simons has authored 2 books and 5 book chapters, co-authored over 180 publications in refereed journals and international symposium proceedings, and 75 NASA technical memorandums. He has been awarded 15 U.S. patents and has received 3 R&D 100 awards for the development of K-band, Ka-band, and Q-band space TWTAs, a NASA Public Service Medal, a NASA Outstanding Leadership Medal, a NASA Exceptional Technology Achievement Medal, and 2 Silver Achievement Medal Group Awards. In 2020, Dr. Simons was selected for induction into the Space Technology Hall of Fame for successful commercialization of traveling wave tube amplifiers. Dr. Simons is also a Life Fellow of IEEE. Following Dr. Simons' presentation, I will be giving a short discussion on how NASA licenses technology to external entities. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation, so if you have any questions, please type them into the chat box in the lower right corner of your screen, and we will answer them during the Q&A session. And now I turn it over to you, Dr. Simons.
Good afternoon, everyone. Thank you, Karen, for that introduction. And as Karen indicated, the title of my webinar is Monolithic Microwave Integrated Circuit Power Combiner. I will start my webinar with an outline. The outline is as follows. I will initially introduce the background and the motivation for this work. Next, I will explain the prior art. I will also point out the limitations of prior art, and then move on to explain in detail the innovation, its advantages, and also I will present the measured and modeled and simulated results. And I will also present the extension of the 2-way combiner to a 3-way combiner. I will also follow up with its measured and modeled results. And finally, I will end my webinar with a brief summary and a list of references that are relevant to this development. Background and motivation. NASA plans to land the first woman and the first man on the surface of the moon in 2024, and also explore more of the moon as part of the Artemis program. Hence, NASA is developing a space launch system shown on the left-hand side here in the picture, an Orion spacecraft to ferry the astronauts to the surface of the moon, shown in the center of this slide, and a gateway, which is nothing but a permanent orbiting space station around the moon, shown on the right-hand side. In addition, NASA is also developing the human lander system, shown on the top side here, which would enable the astronauts to land on the surface of the moon. And while they are on the surface of the moon, to enable communications back to Earth and with the gateway, NASA is also planning on developing a lunar orbiter or a lunar relay satellite, shown in the center of the picture. Furthermore, while the astronauts are on the surface of the moon, in order to enable mobility and also to carry out some interesting science experiments, NASA also plans to deploy a lunar terrain vehicle, shown on the right-hand side. And finally, for the astronauts itself, for their protection and for their extended stay on the lunar surface, NASA is developing modern spacesuits with communications and other sensor capabilities. So all of these systems that I show, which I discussed in the previous slide as well as this slide, require some kind of a comm system, and they in turn require microwave power amplifiers. Continuing with the background, now amplifiers with a few tens of watts at either K-band or Ka band frequencies are adequate for a given data rate and distances that are involved. Shown on the left-hand side is a typical Earth receiving station, transmitting and receiving station. And on the right side is a more futuristic view of a lunar terrain vehicle side by side with a lunar or a moon station. So the distance of separation between these two antennas is on the order of 250,000 miles, 250,000 miles. Now, for communications purposes, the frequencies that have been designated from space to Earth are at K-band and at Ka band. There are also frequencies designated at X and S band, but I will focus on the higher frequencies in this webinar. The near Earth, which means a distance of about 2 million miles from Earth, for that region, K-band is typically used, and the downlink frequency is in the range of 25.5 to 27 gigahertz. For deep space, that is for distances beyond 2 million miles, the downlink frequency is in the range of 31.8 to 32.3. In this webinar, I will present the combiner that we developed in the 31.8 to 32.3 gigahertz range, and I will talk about that, and I will also point out how you can extend that to other frequency ranges. Prior art. Now, amplifiers come in different flavors. You can develop them using vacuum electronics like traveling wave tube amplifiers, klystrons, and etc. Or you could use semiconductor devices like gallium arsenide, silicon, gallium nitride, etc., or a combination of the two, which is called as a microwave power module, where you have a high power end, which is a vacuum electronics, and the low power end is the solid state version. In this webinar, I will focus on solid state power amplifiers that are capable of meeting the requirements that I pointed out earlier. So in a solid state power amplifier, typically, the output from several monolithic microwave integrated circuit power amplifier chips are combined to achieve few tens of watts. The reason for combining is because the output delivered by a single chip is limited to few watts. So if you require several tens of watts, you have to combine them in an appropriate number. Shown on the bottom of this slide is a cartoon that shows the general architecture of a solid state power amplifier. Now in this example, the incoming signal on the left-hand side is divided 4 ways, and I'm assuming, let us say we have 4 chips that we need to combine. The input signal that is divided 4-way excites the 4 mimic chips, and at the output you have a 4-to-1 power combiner. That means the combiner takes at its input four of the outputs from the mimic chips and combines them into a single high power output. So that is the basic architecture. So in this webinar, I will focus on the development of our novel power combiner for such an application. Prior art continued. In the prior art designs, people typically used either a waveguide short slot coupler, which is shown schematically on the left-hand side, or a magic T type of a circuit that is shown on the right-hand side for power dividing as well as for power combining applications. So how does these circuits operate? Now let's look at the short slot coupler first. The short slot coupler has an auxiliary waveguide and a main waveguide, as I've shown there. So let us say that we need to combine the output of two MMIC chips. Those two outputs are brought in as inputs to the hybrid combiner, to the short slot coupler. And one of them is phase shifted by 90 degrees, so that as the wave propagates along the auxiliary waveguide and the main waveguide, they encounter a coupling region, which is nothing but a slot in the common wall that separates the two waveguides. So the two waveguides are joined together along the narrow wall, and they have a common narrow wall with a coupling section or a slot. So through that slot, the two signals combine to give you the combined output. The output on the left-hand side is the isolated port where no power appears. So that is the principle of operation of the short slot coupler. On the right-hand side, you have the Magic T type combiner. So a Magic T type combiner is formed by a junction of four waveguides, as I've shown here. And let us say that we once again want to combine the output of two MMIC chips. The two outputs are fed in the in plane as well as the orthogonal plane ports, which I have identified as port 1 and port 2 respectively here. And the combined power appears on the left-hand side, and the port on the right-hand side is the isolated port. So that is the basic principle of the prior art. But important takeaway here is that you require both the inputs to be identical in amplitude and in phase. That is the requirement. So what does it? It offers certain limitations. Typically, the short slot and the Magic T combiners require MMIC power amplifiers with identical amplitude and phase characteristics for high combining efficiency. However, due to manufacturing process variations, the output power of MMIC power amplifiers tend to be unequal. That means when you fabricate a wafer, let's say 4-inch or a 5-inch wafer, not all, and it has about 100 chips in it, statistically, not all of the 100 chips have identical power output and phase. There is a statistical variation across the wafer. So what do you do with it? Do you discard the chips? It is a very expensive process to do that. So it lacks that, it has that disadvantage that it requires equal power input, the prior art. And the third thing is that lack of flexibility. When a need arises to combine the output from two different MMIC PAs with unequal output power to achieve a target power level, for example, a target output of 15 watts, they need to combine, there may be a need to combine a 10 watt PA with a 5 watt PA. So that is not possible with the prior art design. That's one of the limitations because of lack of flexibility. So that brings us to the innovation. Our innovation is a novel two-way Ka band branch line hybrid with arbitrary power combining ratio and port impedances. That means the two input signals could be not necessarily, it's not needed to be equal, but it can be unequal, and it could be arbitrary ratio. It could be 1.5, 1.75, 2, or any other number. And also the port impedance need not be 50 ohms. It could be anything that the output of the MMIC provides, because I will point out later, I will show through examples that you can impedance match it very well. So what you see here in the center is the fabricated two-way Ka band branch line hybrid unequal power combiner in an E-plane split block arrangement. That means, the two halves are like a clamshell, and they can be assembled. So you can see here, I can quickly point out that is, if this is my input port, the port on the left side, then the two output ports are, then the two ports on the right hand side are the output port, and the fourth port is the isolated port. When these two halves are mated together, the assembled dimension of the combiner is about 2 inches in length and about 1 inch by 1 inch in cross section. So it is very compact and lightweight, and it can handle high powers. Continuing with the advantage is, first of all, is flexibility. It can combine power amplifiers with arbitrary power ratios to achieve the target output power with high overall efficiency. I'm saying higher overall efficiency because if you, going back to the prior art where they had the lack of flexibility, so if you were to combine and go back to my other old example of 15 watts requiring a 10, combining a 10 and 5, if you were to use two 10-watt chips, then you will have to discard 5 watts if you want 15 watts. So that right there itself, there is a significant loss in efficiency. Furthermore, if you were to tweak the output of one of the 10-watt so that it puts out only 5 watts, then also you lose efficiency, as I have illustrated here. So shown here on the left-hand side is the output power versus input power for a typical power amplifier. And on the right-hand side is the power added efficiency on the y-axis and the input power on the x-axis. So as the input power increases, the output power increases, so also does the efficiency increase, till a point when it reaches saturation. At saturation, the output power levels off, and so does the efficiency. So if you were to back off a 10-watt chip to a 5-watt, you lose efficiency as well. Whereas our invention enables both the 10-watt as well as the 5-watt chip to operate at its peak efficiency, and consequently, the overall efficiency is high. Now, second advantage is arbitrary port impedance allows matching MMIC PA directly to the waveguide impedance. Let us say that your MMIC chip for some reason, for design reasons, for maximum power output and efficiency, has an output impedance of 55 or 60 ohms. So you could couple that to a 50 or 55 or 60 ohm microstrip line, and that microstrip line can be used to excite the input ports of the waveguide combiner in two ways. Either you could do it along the transverse plane, as I have shown here. The microstrip acts like a probe and enters the waveguide, and it is backed up by a waveguide backshaft for tuning purposes. Alternatively, the microstrip line could enter the rectangular waveguide along a slit cut along the longitudinal plane of the waveguide. Cutting the waveguide along the longitudinal plane has an advantage because there is the least interruption to the surface currents, and so least amount of losses. And once again, it can be impedance matched by either using a stepped impedance transformer or a combination of stepped impedance transformer and a waveguide shaft. So in either cases, there's a lot of design flexibility here in order to couple a MMIC chip to the waveguide ports. Continuing with the advantage, in beamforming networks in phased array antennas, large number of MMIC chips are used. So the cost and mass can be reduced using additive manufacturing or 3D printing techniques. We can extend this concept. We can take two hybrid unequal power combiners and cascade them together in order to realize a non-binary combiner, that is a three-way combiner. And I will talk more about it later on in my webinar. Now, the combiner design is frequency agnostic and can be realized at any of the microwave frequency bands. In this particular demonstration, as I said, we have picked the deep space frequency of around 30 gigahertz, but this design can be scaled to 20 or 10 or 5 gigahertz based on the needs. And then high combining efficiency. I will talk more about, I have talked about the design aspect of it, how it contributes to high combining efficiency. Later on, when I present the experimental results, I will also point out how the high combining efficiency is achieved. Okay, that brings us to the innovation, the demo results. In this webinar, the design of a Ka band branch line hybrid is discussed, and it is demonstrated that we can combine the output of two MMIC power amplifiers with arbitrary power output ratio. However, for the purpose of demonstration, we present the results for two mimic power amplifiers with output power ratio of 2. But as I pointed out earlier, one could go for a 1.5 or 1.75 or 2 or higher than 2 as well. So schematically shown on the left-hand side is a plan view of the one half of the combiner, where I have identified the various ports. I've numbered them as 1, 2, 3, and 4. One being, let us say, as I pointed out, this combiner is a reciprocal network, so it could be used as a divider also. So let's say that 1 is your input port when it operates as a divider. Then ports 3 and 4 would be the output ports. When used as a combiner, let's say port 3 and 4 are the input ports for the combiner. Port 1 will be the output port where you have the peak power, and port 2 is always the isolated port. Now, in this slide on the right-hand side, as well as in the slides to follow, I will present some of the measured and modeled results to show how well both the modeled and the measured data are in agreement. So, as I pointed out earlier, you could characterize this circuit either as a power divider or as a power combiner. We have done both of them. I will initially talk about how we have done it as a power divider and later on present results for the combiner. So as a power divider, if you are feeding in at port 1 and if you have designed this circuit for a 1:2 power ratio, then the power that would appear at port 4 should be 2 times the power that would appear at port 3. Or in other words, there should be a 3 dB difference between the two power outputs. So that's exactly what you see here on the measured and modeled S parameters here that I've shown on the right-hand side. The simulated, the results are like 1.8, the power that couples from port 1 to 3, and is about 4.8 from port 1 to 4. So the difference is about 3 or in the ratio of 2. The center frequency for this is, as I pointed out earlier, the deep space frequency of around 32 gigahertz. Continuing with the measured and modeled results, I present here excellent agreement where for the input impedance match, the isolation between the input ports and the output ports. So the input port, I'll go back here, very good impedance match at port 1. And then in the center of this chart, I show the isolation between the two input ports, that is port 1 and 2. So between these two ports, port 2 is the isolated port. So between 1 and 2, you have very good isolation on the order of 30 dB. So also there is good isolation between the two output ports, that is ports 3 and 4. There is very good isolation on the order of 30 dB. So, and also you notice that there is very good agreement between the modeled or computer simulated results and the measured results. And moving on to the phase difference, as I pointed out here, we had made the length of port 4 slightly longer so that the power output at port 3 and 4 are in equal phase. So here, when we simulated it, we get perfect phase, that is zero phase difference, perfect results. However, while we were measuring it, we noticed about 20 degrees difference in the phase. I will point out later that the interesting thing about this combiner, it is less sensitive to phase variation, as I will point out later when I present the measured results. On the right-hand side shows the combiner efficiency, which is 94% and higher across this entire frequency range of interest. All right, that brings us to the measured performance, how we went about characterizing and measured results. For the purpose of demonstration experimental results, we used two gallium arsenide MMIC chips with half watt, which is feeding port number 4, and a 1 watt gallium arsenide chip, which is feeding port 3. So they are in the ratio of 1 to 2. So, and at the output port, P out, we get a power that, as I've shown here on the right-hand side, is a plot of the combined power and the combiner efficiency. The output power is close to around 1.4 watts. The perfect, if it was totally lossless, it would have been 1.5 watts. Efficiency is 92% and higher across the frequency range of design. And the phase variation, which I pointed out earlier, we did intentionally put a phase shifter in one of the arms, and we varied the phase to see how sensitive is this to phase variation. And we noticed that for a phase difference of plus or minus 15 degrees, the combined power output, the variation or the change in that was less than 0.1 dB. So that is a very encouraging result that goes to show that this combiner has a very good combining efficiency and very less sensitive to phase variation. Now, this brings us to the three-way combiner. We developed a three-way combiner as follows. We took the two-way combiners and cascaded them as shown on the left-hand side. So port 5 and 6, let us say, are the input ports of the combiner, and port 3 is the third input port. And so port 1 is the combined output power, and port 2 and 4 are the isolated ports. Shown on the right-hand side is the actual fabricated and characterized three-way combiner. Our design goal is shown here on the top. We wanted to maintain the ratio of P5 to P6 as 2, and P3 divided by P5 plus P6 as 2. So that was our design goal. Okay, this shows the actually measured performance. On the left-hand side, it shows our experimental setup, how we went about doing the characterization, and on the right-hand side shows the measured and modeled results. Now, initially, we tested this three-way combiner as a power divider. That means we fed in power at port 1 and measured the power at port 5 and 6 and at port 3. We noticed that the ratio of, although our goal was 2, it had deviated slightly from that, and the ratio of P5 to P6 was around 1.7, and the ratio between P3 divided by P5 by P6, sum of that, instead of being 2, was around 1.67. So 1.7 was the ratio that resulted after we fabricated this circuit. So we decided to test it that way. So we kept the ratio of P5 to P6 as 1.7, and then we changed the ratio of the other power, that is the ratio of P3 divided by P5 by P6, about 1.7. So 1.7, then we went on the lower side as well as on the higher side, and we generated this curve. And we noticed that the efficiency peaks, it's around 92%, a little higher than 90% when the ratio of P3 divided by P5 plus P6 is 1.7. And you also noticed that the design is a lot forgiving. Although we had designed it for 2, but it resulted in 1.7 ratio. But when we tested it, the efficiency is greater than 90% over a wide range of power ratios. That is something new that we understood after we did these experiments. Okay, that brings me to the summary of my webinar. So I will quickly summarize this. A novel Ka-band rectangular waveguide branch line hybrid with arbitrary power combining ratio and port impedance is presented. As an example, a two-way combiner that combines input signals which are in phase and with an amplitude ratio of 2 is demonstrated. A solid-state power amplifier with such a combiner requires fewer MMIC power amplifier chips for a target power output, which is a cost advantage. A combiner has excellent return loss, isolation, and combining efficiency. And finally, a three-way combiner is also demonstrated. So that brings me to the list of references. These are list of references which essentially talk about our patents, the combiner and the divider patents, and then several of the refereed journal and international symposium papers and NASA TMs. Thank you very much for your attention, and I will be glad to answer any questions that you may have.
Thank you, Dr. Simons. That was a great presentation.